Okay, so from here, the next thing we're going to do now is we're going to draw the XY plane. Right? So when in this case, this will be our Y, this will be our X, and then using right-hand rule, okay, when we use right-hand rule, this is rotation in our Z. Okay. So now I'm going to sketch the structure now. Now the structure looks like this. Okay, so the structure look like this now. And then we have our geometry centroid. And then we have a load over here. This will be our PX. Right? So now how this structure will deform now is this structure will deform, not deform, buckle this way. Okay. So now we know over here, this is your RZ, right? You draw the circle because of the rotation, right? So we know that based on the curvature and the curvature over here is the same. So when that's the case, our critical load becomes pi squared E multiplied by IZZ over what? L squared. From here, I'm going to take the same image like we had before. You now have to determine which is the width and which is the depth. So from here, we know that this is the Y and this is the what? The Z. Now, the axis of interest is your what? Your axis of interest is your what? ZZ. Can you tell me which is the width now? Now I'm going to draw this direction. This direction, is it the width or the depth? Anyone? Well done. And this direction is the what? Right? Anything that's perpendicular to the axis of interest is going to be your what? Depth. Simple. Okay. Done too many questions on this sort of problem. Follow this technique. You will not get wrong. Are we clear? Right? Okay, or not, it's pretty confusing. Anyone, any questions? Okay, I don't hear any question. So when that's the case, note buckling will occur with the lower second moment of area, assuming the end conditions are the same. Okay. When we assume the end conditions are the same, okay, what do we mean by end condition? So the end conditions are, for example, for this case, the end conditions are what? It did not specify, but the end condition for this case I'm going to put the load P down here. Okay, so this is pin, and the other side is what? Pin. So this over here is known as the end conditions. Okay, so now let's try to look for our second moment of area. So what we're going to do now is we are on this side, we are going to focus on IYY. Okay, IYY. So the axis of interest this is our width, or this is our YY. So this will be our width. And over here, this will be our depth. Now, there's a terminology that I want you to be familiar on, okay? Any horizontal component is known as our flange. Over here, this is also our flange. Any horizontal component is our flange. Any vertical component is going to be our what? Our web. Okay. So we're going to determine IYY. So IYY will be equal to the width depth cube over 12 plus by width multiplied by depth. Okay. Then we're going to have our capital Z bar minus the small z bar. Okay. Capital Z bar denotes the global centroid position. The small z bar is the individual section centroid position. Okay. So it happened in this case, right? It happened. So I'm going to drop the transformation again. This is our y, right? And then this is our z. Okay. So if we were to look visually, okay, by visually, we know that this green line, right? This green line is also known as our what? Also known as our global, I beg your pardon, okay, global and individual centroid. Okay. So they coincide one another, right? So when they coincide one another, what will happen to this term is this term will be equal to what? 0. Now, this geometry, you can determine the centroid visually. Are we clear? Sometimes you can't. For example, like a T section, you can't. Okay. So when that's the case, you can find IYY is equal to twice IYY of the flange plus IYY of the web. Okay. Twice of the flange because you have a top and you have a bottom. So twice. Then you have the width is 9.5. The depth is 40. Power 3. Hey, sorry, the 3 not very happening today. Divide by 12. Okay. Plus the width is equal to 120. The depth is 9.5. Divided by 12. So from here, this will come out to be, yes. Total length is 80. For the web or the flange? Ah, yeah, you're right. Thank you. 1 pint. Come to my office. So what we have is 819.24 times 10 to the power 3 millimeter power 4. Okay. Then when you convert this, it'll be equal to 819.24 times 10 to the power minus 9 meter to the power 4. Now in this course, okay, all your answer have to be left in terms of 10 to the power 9, 10 to the power 6, 10 to the power 3, 10 to the power minus 3, 10 to the power minus 6, and 10 to the power minus 9. Are we clear? I don't want to see 10 to the power minus 5. I don't see 10 to the power minus 7. I don't want to see 10 to the power 7. Are we clear? Why is that? Why we have to use engineering units? So when you do conversion, it's going to be much easier. Are we clear? Or not, it's going to be mayhem for you and for me. Okay. Right? Right. So now you can see what we have for IYY. Okay. So next, we're going to deal with IZZ. Okay, next, we're going to deal with IZZ. Okay, let me copy. Let me get this out. So next, we are going to deal with IZZ. Okay, we're going to deal with IZZ. And again, the formula is width depth cube over 12 plus by width multiplied by depth, capital Y bar minus small y bar. And then we have a square. So now we are aware that the ZZ axis is the axis of interest. And where I am drawing now, that is the position of the centroid also. And this is by visual inspection. So from here, again, the most important thing to do, okay, the axis of interest is ZZ. This is going to be the width. And this is going to be our depth. Okay. So now we are no more confused. Okay. Very important not to be confused with all this. Okay. So now we are going to do the top and bottom flange. So IZZ for the flange, the width is now 80. The depth is 9.5 cube divided by 12. Plus by the width is 80. The depth is 9.5. And then the global centroid is equal to 60 plus by 9.5. And then we are going to minus by 9.5 divided by 2. And then the whole thing squared. So why 60 plus 9.5? Because the distance from here to here is 60 plus 9.5. Yes or no? The 9.5 is the other small part. Okay. And then why we have to do 9.5 divided by 2? Because over here, the position from here to here is 9.5 divided by 2. Okay. So that's how we determine is the global centroid multiplied by